Suppose David and Jean take a mortgage, i.e. a loan, now, of €200,000 to buy a house. They agree to repay this loan plus interest by a series of equal monthly payments, starting in 1 month's time and continuing for 20 years. The effective annual rate of interest is 6%. Part 1. Find the monthly interest rate that is equivalent to an effective annual rate of 6%. Give your answer in decimal form, correct to 8 decimal places. So we're going to use the compound interest formula, which is found on page 30, which is P equals A times 1 plus I to the power T. We're going to let I be the rate per month that is equivalent to 6% per annum. So we have our annual rate is P equals A times 1 plus 0.06, because the interest, is 6%. And then the monthly rate is P equals A times 1 plus I to the power 12, because there's 12 months in the year. So this is what we're trying to find, this I. Since they're both equal to P, we can let them equal each other. So we have A times 1 plus 0.06 equals A times 1 plus I to the power 12. We can cancel out the A's, so we're left with 1.06 equals 1 plus I to the power 12. So 1 plus I to the power 12 equals 1.06. So 1 plus I is equal to 1.06 to the power of a 12th. So 1 plus I is equal to 1.004867551. So I is equal to 0.00486755. Part 2. Use geometric series to find the monthly repayment David and Jean have to make on their mortgage. So we're going to let A be their equal monthly repayments, and let V equal 1 over 1 plus I, which is going to be 1 over 1.00486755. We got this number in part 1, which gives us 0.99515,60277. So 1 over 1 plus I, this is the common ratio, and we got this from the equation of value. So 1 over 1 plus I is what you multiply each of these terms to get to the next. So the common ratio between each term is 1 over 1 plus I, i.e. we multiply each term by 1 over 1 plus I to get to the next. So taking the focal date to be the date of getting the loan, the present value of their loan is 200,000. They will have to make 20 times 12, which is 240 repayments, starting in 1 month's time. The present values of their repayments can be laid out in the form of a table. So our first column is the payment number. First payment, second payment, third payment, ... down as far as the 240th payment. The second column is the value. The value is always going to be A. The third column is time in months. 1, 2, 3, ... down as far as 240. So there's been 240 months or 240 repayments. And the fourth column is the present value. So where did we get all this from? Well, if this is now, and this is in 20 years' time, then we're discounting backwards to now, the focal date. So if we're discounting backwards by t years, we divide by 1 plus I to the power t. So this is going to be our formula. So A over 1 plus I to the power t, which is the same as the equation value. Each term of the equation value is in this form. So when t is 1, we just have A over 1 plus I. When t is 2, we have A over 1 plus I squared. When t is 3, we have A over 1 plus I to the power 3, and so on. And when t is 240, we have A over 1 plus I to the power of 240. Now in the previous slide, we stated that V, which was the common ratio between each of the terms in the equation of value, was 1 over 1 plus I. So to multiply 1 over 1 plus I to each term to get the next. So we can swap the 1 plus I, which is really 1 over 1 plus I, for V. So for example, A over 1 plus I can be rewritten as AV, and A over 1 plus I squared can be rewritten as AV squared. and a over 1 plus I cubed can be rewritten as av cubed. And likewise, a over 1 plus I to the power of 240 can be rewritten as av to the power of 240. So remember, for the equation of value, the key principle behind financial transactions such as these is that the sum of the equivalent values to all advances or borrowings at any focal date is equal to the sum of the equivalent values of all repayments at the same focal date at the going rate of interest. So by the equation of value, we're going to take all these terms, we're going to add them together, and we're going to let them equal to 200,000. So we have AV plus AV squared plus AV cubed plus dot 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 plus AV to the power 240 equals 200,000. So here we have a series. So we're going to use our series formula from page 22, which states that Sn is equal to A times 1 minus r to the power of n divided by 1 minus r. So the A is going to be AV because that's our first term. So we swap this A for AV. Then we have 1 minus r. So the r is going to be equal to V. So the rate is now V. So we have 1 minus V and 1 minus V. And the n is going to be 240. We have 240 repayments. So we have V to the power of 240. And that's all equal to 200,000. Next we substitute 0.99515,602.77 in place of the V. We got that from the previous slide. So we swap this V for that number, this V, and this V. So we have A times this is all equal to 200,000. So that ends up giving us 141.384309A equals 200,000. So we get A is equal to 1,414.58. Thus, their monthly mortgage repayments are €1,414.58, correct to the nearest cent. And just a reminder, this is the official definition of the equation of value. Part 3. Use the amortisation formula to check your answer to Part 2. So P is 200,000, I is 0.00486755, we got that in Part 1, and T is 20 times 12, which is 240 repayments. So 20 years times 12 months is 240 months. Thus, the monthly repayment A is given by, this is on page 31 of the formula book. So A is equal to P times I times 1 plus I to the power T divided by 1 plus I to the power T minus 1. So remember, we're swapping the P for 200,000. We're swapping the 3 I's for 0.00486755. And we're swapping the T for 240. So to the power of 240 on the top and the bottom. And that ends up giving us €1,414.58. Thus, their monthly mortgage repayment is €1,414.58, as in Part 2.